Hey guys, this is going to be part 5 of the USB hub series. This should be or will be the last part of the schematic, and then we'll go into the actual PCB layout. This video is going to cover mainly the input filter on the 12 volt line and ESD protection on the upstream and downstream USB ports, and just a couple little things here and there. And before I jump into the video, make sure you click the link in the description below and join the Discord if you have not already. Okay, so the schematic is pretty much where I had left it, with the exception of a few things added to the USB hub and then this USB Type-C filter. The first thing I want to mention before going in anywhere else is, so on the USB hub itself, the data lines on the downstream ports, they actually support, and I had mentioned this briefly, the battery charging protocol, which, and this is where I've mentioned it a few times, the standards with USB is are a complete joke. Like Apple, Samsung, Google, everybody uses different protocols for power communication. So unless you're building something for a specific device, it's really a crapshoot, and you just kind of want to do the best you can. So this supports the battery charging 1.2, which allows it to have up to 1.5 amps with data. But in reality, this is now kind of changed to 1.9 amps. But again, it really depends on what you're charging. So for this, I had been mentioning that these I'm planning on rating for 3 amps each, which I'm doing. Everything is still the input buck, the input power supply. Everything will still be rated for 3 amps. But unless a downstream device is violating the BC protocol, which they very well could, realistically, these are only never going to be drawing 1.5 up to 1.9 amps. So realistically, this is a little bit overkill what I had done in the buck side, but no harm, no foul. It just means it'll be a little bit overbuilt, which better that way than the other way. So what's nice about that is that means on the downstream ports here, it handles the communication and the negotiation to talk to the downstream device to make sure that it can, or it can acknowledge that it can draw that much current. So typically on the data lines, you would need to have your 15K pull downs to say that it is can source power, and then to do the BC protocol, you actually have to have other logic on here, but we don't have to worry about any of that. The hub hopefully handles that. So from there, on the upstream side, for the shield and ground, and I guess also on the downstream side, this is another thing that there's no real good standard, and someone in the comments made a good point about this. So in an ideal situation, the upstream device is grounded and shielded, and it basically extends its shield to the downstream device. So you can think of if it's a shielded cable, you can think of it essentially being a Faraday cage around the cable, which extends to the enclosure on the downstream device. And by tying this upstream facing port, the shield, to ground, I'm essentially breaking that, and you can have ground loops flowing in that shield. So realistically, if everybody is playing by the rules, the shield should be disconnected, or you can do a RC filter, or sometimes a ferrite. But what I typically will do is still ground it, and then have a jumper so you can kind of play around with it. But again, the upstream facing device in theory should not be grounded on the shield, not at least DC. And then on my downstream devices, these absolutely should be grounded on the shield, because that gives us our Faraday cage on the USB cable to the downstream device. So this block is the USB-C filter, and I did it the same way as I've done all the other blocks, just labeling what comes in and out. And all of these are just pass-throughs, and then we have sets of TVS diodes. So when it comes to protecting I/O lines on a high-speed device from ESD events, it is a whole different world than when you're dealing with like low speed or just logic level. And the primary reason for that is the capacitance that is on those TVS diodes. So I have a TI data sheet. So, and this is another thing with USB Gen 2, there's no hard and fast rule on how much capacitance is allowed. So the best rule that I basically have is make sure you're using a TVS diode that is rated for at least the speed of the interface that you're using, if not faster. And the way that they kind of test these is it's what's called a eye diagram. And an eye diagram is just a transformed logic signal inverted. And you make sure that it's a crisp signal as compared to this, which you can obviously still see where the logic signal is, but it's super blurry. Everything melts together, and you're not going to be able to run at full speed if it looks like that. And this is USB 3.1 Gen 2, so exactly what we're doing. And this is a 0.5 picofarad TVS. 0.5 picofarad is pretty small, but like I had said, it presumably wasn't rated for it. Whereas this one with TVS diodes that are rated, your eye diagram is still pretty crisp. And what you'll notice, this is a TI part, so obviously they're going to make the testing look super favorable for them. But in reality, with every TVS diode you add, it degrades the signal. It's unavoidable because you are adding capacitance. So that whole summary aside, you still really do want to have some protection on these high-speed lines. But you have to understand that the faster you get, the less robust these protection interfaces are going to be, and you just kind of have to live with it. Whereas if it's a slower speed, or like my V-bus here, we can use a beefy 9.8 amp clamping TVS diode. Here it says 16 amps, but obviously we know how well those rate. So for the TX and RX lines, and this is a on semiconductor part because TI was out of stock on all of theirs, naturally. And this is rated for USB 3.1 Gen 2, and I believe even HDMI. So we shouldn't have a big issue there. But in testing, one of the first things, if I have an issue with a high-speed interface, the first thing I do is remove the TVS diodes and then test without it, just because, again, that's a pretty common place for there to be an issue. The CC and the D+, D-, they did not have to be on this low of a capacitance array, but since these are already going to be susceptible using them anyway, and I didn't want to add extra parts, having 4 of these, I just threw them on the same lines as well. And then on the V-bus, just standard 5-volt TVS here. And then another important thing with a USB device is the downstream capacitance. So since this device is connected to an upstream device, there's a limit on the inrush current that can be shown to that device. Because if this basically had, if the V-bus line had, say, like, I don't know, like over 100 microfarads of low ESR capacitance, so say we had like 22 microfarad ceramics paralleled all throughout here, when you go and plug this in, this device is going to draw a crap ton of current the second you plug it in, and depending on how the upstream device is configured, it could blow a fuse, it could cause massive ringing with an overvoltage event. So USB has a spec on that. You cannot have directly over 10 microfarad capacitance applied. They allow, obviously, an inrush limiter. So if you had an inrush limiter, like right here, like one of those little series ICs, then you could have as much capacitance downstream of that as you wanted, because that series device is obviously going to limit it. Since this VBus isn't actually powering anything, it's just used for the VBus detection, it doesn't matter, and I just threw some on here just to help smooth any transients out. But we're at 4.4 mics, well below that 10 mic limit. And then on the downstream side, it's basically the same thing. The same TVS is here, everything passing through. Now, since this is an upstream facing port, there's really no limit because on the capacitance, because as long as you are accounting for any ringing from these being low ESR, which I am with the TVS, the downstream device is limited to 10 mics, so we should be fine there. And further, we are also using this VBus monitor, which handles overvoltage and overcurrent internally. So even if the downstream device violates the USB protocol and does what I said before, has over 100 microfarads of low ESR capacitance, the VBus monitor here will take care of it, no problem. That's why you use these, because like I keep repeating myself, the USB standard is just a complete cluster. So that's why these little monitor chips and everything exist, to handle when devices violate that protocol. So that is the bulk of the, and sorry if I kind of skimmed over that, I have, and I'll link in the description and up above, I have another video covering ESD protection, so I just don't want to be super repetitive. And there's a million different ways to do it, but for a high-speed interface, this is kind of the bog standard way to do it. And then the next thing I want to jump to, and this, just because there's a lot here, I'm going to brush over kind of quickly too. Look in the future, I'm going to have a pretty big series on some EMI considerations, and this is going to be a pretty big one. So on the 12 volt input line, we have two buck converters on it, which bucks, as I've talked about while designing these, you have a lot of ringing noise on the, or switching noise on the input side, because the FETs are on, off, on, off, on, off, and you get that voltage drop each time on the input side from parasitic inductances and resistances. So you add a big parallel capacitor array to help supply that and to help smooth it. But that can only do so much. And one of the biggest, if not the biggest reason that a device will fail EMC testing is the cable's radiating noise. You have to keep in mind that a PCB, even if it's big, you're talking a device like this, like 3-4 inches by 4 or 5 inches, maybe 10 inches at its biggest. Even if you mess up the layout really bad, it's a pretty small antenna, so you definitely can, especially when you get into high-speed devices that have really high harmonics, you can absolutely fail based on the PCB itself radiating. But look at the cables. The cables, you have 2, 3, 4, 5, 10 feet of a literal antenna going out into space. Almost every EMC issue that you'll see, even if the PCB itself is radiating and fails EMC testing, it's failing way worse on those cables. So when you have a buck that puts the noise on the input side, you really have to, and overgeneralization, but if you're going to pass EMC testing, you pretty much have to have some sort of input filter, whether it's common mode choke, an LC, ferrites, you have to have something. So what I did here is I did a pretty kind of like the best case scenario if you have the space, if you have the money, all of that, because obviously this USB hub is pretty overbuilt as is. So what I have is a LC filter that is damped on the input side to prevent oscillations and a common mode choke. The easiest thing is the common mode choke, which, and this is another thing I'm not going to go into, but throughout the rest of the board, mainly again on the 2 bucks, you can have a differential to common mode noise conversion, which means on our 12 volt line, we're going to have common mode noise radiating on the input, on the positive, and on the return side, radiating off onto the cable out into space. Differential noise causes signal integrity issues. Common mode noise causes EMC issues. So by throwing in a very beefy common mode choke, that helps eliminate the bulk of the common mode noise. Having the two 1 mic ceramics on either side helps filter the differential noise. So that's super easy. The advantage of this, other than being very, very effective, is you don't really have to worry about any side effects. You throw a common mode choke, yes, you get a DC drop, obviously, because it's anything. It has parasitics, but you really don't have to worry about any oscillations, any ringing, anything like that. The next thing is an LC filter, which an LC filter, while being a fantastic differential mode filter, an LC filter obviously has a resonance peak. And if you don't damp it with a resistor and there happens to be something on the board that's exciting it at that resonance peak, you can make the issue that you're trying to solve significantly worse. So when I am going to do an LC filter, there's two or three main considerations that you want to sort out. The first one is what size inductor do you want to use? And as a overgeneralization, but it holds true pretty much for everything, is the larger your inductor, the better job of a filter it's going to do. And that's kind of obvious. The same with your capacitors. The bigger anything of your filter can be, it's going to be more effective across larger frequency ranges. But there's a big issue when you make it too large. It now requires all of your inrush and all of your bulk capacitance to be on the other side of that inductor. Because let's say if this was like a 4.7 microhenry inductor, any of your transients on this side, they're going to be blocked by this completely, which, yes, that's the goal, but it also means you're going to have such a large bulk capacitance array out here, it's not feasible for your board size. So like anything, it's a trade-off. Anywhere from like 220 up to, or 220 N up to like 1 or 2 mics is a good range. This draws a lot of current, obviously, so I couldn't go with much bigger than this. And then the equation to actually determine how much bulk capacitance you need is, there's a great, and it's on a few different places, but this TI app note is pretty fantastic. And basically what you do is on all of your buck converters, you determine what the maximum input transient would be. So in our case, how much current is each of our bucks going to draw from the 12 volt? Nothing else on this board draws from the 12 volt, so that's all we have to worry about. If we had other components on that 12 volt rail, obviously we would have to worry about them, but we don't. So we take the current input side of all of our bucks, add them together. That gives us our total transient on our 12 volt line. Then using this equation, which I've used this equation for years, and I never really looked into a ton of where it's derived from, And I asked about it on the Discord. This is just a side note. I asked about it on the Discord, and a member, Ahid, sorry if I'm pronouncing it wrong. He actually went into the full derivation. Super, super useful. Another reason to join the Discord. But basically, what this does is it takes into account the input transient and determines, based on the allowable voltage drop, what size of bulk capacitance you need. So what that's saying in a nutshell is, if we didn't have any bulk capacitance here, anything that's drawing current on this input side above the frequency of the LC filter cutoff range isn't going to be able to draw anything from here because it's blocked, and all of that current will have to come from the input caps from the buck. But when they run out of charge, there's a drop in your voltage rail. So what the equation is saying is, what is our allowable voltage drop? And I always use 0.1 volts up to like 0.25. This I did 0.1. So I calculated the input transient on the 5 volt and the 1.15 buck, which comes out to 4.5 amps, but I didn't bother taking into account this, so I just bumped it up to 5 amps. And then using the equation, it comes up to 665 mics. And a big asterisk with this equation is, this is like the absolute lowest. So if you were to have 670 mics of capacitance, that would just barely be enough if all things are working well. So you want to have at least like 50% over. Here I'm using two 470s, so I'm 50-ish percent over plus the 22. I could probably add another 470 here to be safe. But until you test on your oscilloscope or spectrum analyzer, it's just kind of a best guess, but it's way better than just shooting in the dark. So now at this point, designing this filter, we know what our bulk capacitance is. We know what our input inductor is roughly. We just kind of have that based with what's in here. And what I'll usually do is iterate this and say, oh, if I change the 220 nanohenry to 470, can I handle that much bulk capacitance? No. Okay, then lower it and just get it to where the bulk capacitance isn't obnoxious. So now at this point, we have this sorted. We don't know what we want on the input side, and we especially don't know what our damping resistor would be. So this is where Spice comes in handy. And I'm already, this is going to be a long video as is. I'm not going to go into a ton with Spice, but basically, and this is the way I test all of my decoupling arrays. It's how I test my filters. It's with what's called a small AC signal analysis. And in a nutshell, what it is it's basically just testing what the impedance of a circuit is. So what is the essentially resistance from our power source to ground at varying frequencies. When you're testing it in the way that I'm doing, you want to have the gain as low as possible for as much of the frequency range as you can, because this is 1 mic or 0.1 mic capacitors. You want to have a super low gain so any microcontroller on this rail can grab current from these capacitors with as little inductances and resistances as possible. The one note with this, like everything else, this is really relative. So you can't compare and say, oh, I need it to be under 70 dB, because I am making an assumption on what our power supply resistance is. I'm making assumptions on the small signal analysis holding true. So all it is as a comparison, and to make sure the relative values are acceptable. So for the first example, this is using SimSurfer to grab the exact capacitors that I have on each of the input converters, on each of the bucks, and it's at the bias voltage that they're at on the circuit. So it's about as good as we can get. It takes into account the parasitic inductances and resistances. So we have our array here, and then it shows again our RC or AC small signal analysis, and it shows that our impedance is the lowest at 2.5 megahertz, which again, you can't really look at absolutes because depending on what our input power supply is, depending on what else, all we know is that anywhere from 1 to 10 megahertz, our impedance is pretty low. So our buck converters, their switching frequency is, I believe, 2-ish megahertz. So that looks pretty good. Now our other example is the filter that I have in KiCad already drawn, except without our damping resistor. So it doesn't have our 510 milliohm resistor, and then it doesn't have the common mode side because that really doesn't affect this too much, or it shouldn't, other than the parasitics. So now if we look at our frequency graph here, you can see it's a night and day difference. I mean, the gain is from 100 dB down to almost 160 dB. Again, not absolutes, but what we can see with this is having that LC filters out the signal incredibly well compared to just the decoupling or just the capacitor array, which this is, again, commonly well known. Like I said, if you don't filter the input supply when you have bucks, it's not going to pass EMC testing. So whatever this real world gain would be is probably not good enough to pass EMC. So down here, that makes you feel a good bit more confident. But what is this? This is that nasty little resonance peak that I was mentioning. If you happen to have something on your board that excites it at 80-ish kilohertz, you're going to have a peak on your frequency response at this point. That is where we go ahead and add a damping resistor here. I guess that's why sometimes it's good to double check before the video. So I actually made a few changes to the input side of this filter. So this is what I was going to be showing as the big improvement over just the 222 mics, but it actually wasn't much better. There was a much better improvement of just adding a third ceramic. So this filter right here is the bright green, and then the one that I was using is the teal or whatever color that is. The key is with this, again, keep being repetitive, but you can't take this as absolute, is you want to make sure whatever your little resonance peak is, it's below what it would be if you weren't using the filter, and it's not at the same frequency as your bucks. Because if we were using one of those TI like simple switchers or something that has a super low frequency and it was somewhere in here, that could be really bad, because if we are slightly off with some of our values here and this is peaking higher, you could be making it way worse. So that's kind of the main thing to keep in mind with these filters. So even though the simulation showed that the 510 here wasn't needed, I'm still going to have the footprint on at least one of them in case when I do the testing it shows that there is some resonance without that. I can always damp it down the road. You can do that, or another good approach is to have a footprint for an electrolytic, because an electrolytic has a high enough ESR that it can help damp it. But with the low value of the inductor, as Spice showed, this seems to be a pretty well damped filter as is. So I don't think there's a high risk of getting any resonance. If this was higher, we definitely would. Or if the output capacitance wasn't so large, that could also make it have a higher affinity for that peak. But since we don't, we should be good until testing. So that pretty much wraps up the schematic. Other than a few maybe modifications here and there, I think the plan now is to do to start doing the layout, and I'm probably going to be doing those all on live streams. So if you want to hear more about the schedule and everything for that, go ahead, check out the Discord. I'll be posting about it. And until then, I hope you guys have a good one, and I will see you in the next video.